Hi everybody, I'm Chloe Standridge.
I'm Chris Havard.
I'm Juan Castellanos.
And this is our final presentation over steam sterilization using hydrogen-oxygen combustion.
The definition of this project is our group was tasked to design a sterilizing steam generator using hydrogen-oxygen combustion. A secondary application includes using the generator to power a turbine. References for theory, designs, and calculations were based off of the two reports shown below. Experimentation of the novel hydronic steam generator and experimentation of the HOSG 200K steam generator. The project scope for this project is broken up into three sections. In section 1, the combustion chamber, it begins after the pre-mix nozzle designed from last semester. Base elements include a flame chamber, throat, and mixing chamber. In section 2, transportation, this transports steam from combustion chamber to delivery mechanism. Base elements include the tubing/hose. And for the last section, delivery, this refers to exit nozzle that terminates the transportation mechanism. For the project parameters, the main objective goal of this project is producing saturated steam. In the combustion chamber, it must reach a relatively homogeneous temperature profile before reaching the mixing chamber. And the mixing chamber must adequately mix the two steam products. As for transportation, this must withstand high temperatures and pressures, and depending on the application, this needs to be able to reach the given surface. As for the last section, delivery, this requires a nozzle that can effectively deliver the sterilizing steam.
So we'll just briefly go over the alternatives that were mentioned in the previous presentation. Alternative 1 is modeled after a double pipe heat exchanger with a threading around the combustion copper chamber to encourage a spiral-like flow. The water sleeve and mixing chamber are then added to complete the design. Although this design is foreseeably complex for simulation and manufacturing purposes, the increased surface area would cause a higher rate of heat transfer. Alternative 2 is a counterflow heat exchanger with the copper coiling on the inside of a steel sleeve. The water would be injected, but the flow would be the opposite direction of the flame. Again, this introduces the same complexities, but the nature of the flow also increases the rate of heat transfer. And here's a little schematic that shows the details of Alternative 2's design. Alternative 3 is a simple design closely related to Alternative 1, except there's nothing modeled to control the flow of the water, which can result in the sleeve overflowing if there isn't a high enough rate of heat transfer. So one of the biggest pieces of advice that we took from our midterm presentation Q&A session with the faculty was that we really needed to ensure that we were picking the right alternative because of the complexity of manufacturing as well as the price that it was going to take in order to produce our project. So we decided to make two extra Pew matrices, one having to do with the heat exchanger, going through with the manufacturability, maintainability, analysis, and cost. We actually came up with Alternative 3 being the best option. Then we also made a Pew matrix over the mixing chamber, and Alternative 2 and Alternative 3 became tied in the end since they were pretty much the same.
And this is our final design. We chose elements from the third alternative with a simple heat exchanger. And for the mixing chamber, after several discussions with our client, we decided on baffles to provide the mixing of the two fluids. Water injection occurs via direct injection into the annulus between the shell and the tube, where the stream hits the curvature at a tangent and cycles around the heat exchanger.
So in order to move forward with the manufacturing process, we decided to run a few experiments with the premix nozzle that was designed in the previous semester so that we could have an idea of what the flame length and width were, the temperature, so we could decide on the dimensions for our combustion chamber. So the first experiment we ran with just the premix nozzle, nothing attached to it, at 85 SLPM of hydrogen. and the flame width came out to be about 1.988 inches. So we decided that the pipe diameter should be about 2 inches because we wanted it as close as possible to the inside of the chamber walls to encourage the best heat transfer. So in the previous test, we also found the flame length to be about 12 inches long, so we went with a copper pipe that was also 12 inches long. And in this next experiment, we attached the pipe itself and ran the same test at 85 SLPM of hydrogen and found the surface temperature to be 1,550 degrees Fahrenheit, which is about 842 degrees Celsius.
To determine the size of the heat exchanger, we need to examine how much heat flux is occurring. To do this, we will use a theory that heat flux flow boiling is estimated as the sum of the heat fluxes of internal forced convection in the appropriate regime of pool boiling. There are 4 regimes of pool boiling, and the one we are concerned with is film boiling, as that is the regime that produces 100% vapor. Another regime, radiation boiling, becomes applicable for surface temperatures over 300 degrees Celsius. To determine the heat flux for forced convection through an annulus, we must find the convection heat transfer coefficient. Here, we are given the preliminary steps of the hydraulic diameter, the Reynolds number, and the friction factor. Given these values, we can also find the Nusselt number, and by extension, the convection heat transfer coefficient, which comes out to 1,765 watts per meter squared Kelvin. Using these values, as well as a correction factor for flow through an annulus where the outer wall is considered adiabatic, we can find the heat flux for forced convection, which comes out to 1,117 kilowatts per meter squared. Heat flux for film boiling on a horizontal cylinder is given as such, where all liquid properties and the enthalpy of vaporization for saturated water are evaluated at the saturation temperature of 152 degrees Celsius. This is the saturation temperature due to a gauge pressure of 5 bar. All vapor properties are evaluated at the film temperature of 497 degrees Celsius. With these values, we come out with a heat flux of 141.2 kilowatts per meter squared. Heat flux for radiation boiling is given as follows, where epsilon is the emissivity of the heating surface, which is the copper heating element, and sigma is the Stefan-Boltzmann constant. Here we find that we have a heat flux of 3.217 kilowatts per meter squared. The total heat flux for flow boiling is given as such. The forced convection plus film plus radiation boiling. Due to the adverse consequences that occur between film and radiation boiling, a correction factor of 3/4 is utilized and recommended. With this in place, we find a total of 1,261 kilowatts per meter squared. Now that we've found the total heat flux that we have, we need to find the total heat flux we need to evaporate water from liquid to vapor. The rate of heat transfer required to evaporate a given mass flow of water under a 5 bar gauge pressure is given as the sum of the sensible and latent rates of heat transfer. Sensible heat is that which changes the temperature of the fluid with no phase change. Latent heat is that which provides the change in phase from liquid to vapor with no change in temperature.
Engineering equation solver was then used to solve for a sufficient water mass flow rate of our system. The inputs were chosen to produce a steam exit temperature of 300 degrees Celsius plus or minus 10 degrees Celsius. This value was chosen by the customer as the highest desired temperature of produced steam. Selected inputs include 85 LCPM of H2 and 0.078 gallons per minute of water. Here is a screenshot of engineering equation solver with our given inputs. We as a group felt that it was user-friendly as it provided us effective calculations. For the given inputs, the program returns a steam exit temperature of 294.1 degrees Celsius, which falls within the desired temperature range. Thus, for 85 LCPM of hydrogen, 0.078 gallons per minute is determined to be an adequate water mass flow rate.
Now that we have an adequate mass flow rate of the water, we can find the sensible and latent rates of heat transfer, and they are given as such. The specific heat of saturated water is calculated at the bulk fluid temperature of 88.5 degrees Celsius. Enthalpy of vaporization is calculated at saturation temperature of 152 degrees Celsius. With all of these values, we come up with 11.80 kilowatts. Now that we have both heat fluxes, the heat flux we have and the heat flux we need, the total length of the heat exchanger element can be determined by comparing these two values. With a known diameter, we can algebraically solve for the unknown required length. The ratio of total and needed heat fluxes to find the heat exchanger length are given below, where the heat fluxes can be expanded into their rates of heat transfer divided by their respective surface areas. This is how we determine the length of the heating element. This comes out to 2.02 inches, though the flame length of this combustion chamber is roughly 12 inches. Thus, the conservative choice is the 12-inch length. We can now examine the heat exchanger effectiveness. The effectiveness of the heat exchanger can be found by dividing the actual rate of heat transfer by the maximum possible rate of heat transfer. We begin by investigating the mass flow rate of the superheated steam from stoichiometric mass balance. Due to the mass balance in the premix nozzle, the sum of the inlet mass flow rates must equal the outlet mass flow rate, which is the mass flow rate of superheated steam that exits the premix nozzle and enters the combustion chamber. The stoichiometric balanced equation from earlier states that for every mole of hydrogen gas, half a mole of oxygen gas is required for complete combustion of the fuel. Thus, for the given volumetric flow rate of 85 standard liters per minute of hydrogen gas, half of this flow rate, or 42.5 standard liters per minute of oxygen, is required for complete combustion. We can then multiply these volume flow rates by their respective densities taken from 25 degrees Celsius and 5-bar gauge pressures of the gas cylinders to determine their respective mass flow rates. We then add these together to find the superheated steam mass flow rate, which comes out to 0.005141 kilograms per second. The heat capacity rates of the cold and hot fluids are given below. The mass flow rate of the cold fluid was determined by the engineering equation solver program, which determined an adequate value of 0.004921 kilograms per second of feed water. The specific heats are taken from the respective inlet temperatures of 25 degrees Celsius for the cold fluid and 477 degrees Celsius for the hot fluid. With all of these values, we can now calculate for both rates of heat transfer, given by the equations below. 152 degrees Celsius is the saturation temperature for water due to the 5-bar gauge pressure of the steam generator. The 477 degrees Celsius is taken from studies, where for our range of hydrogen gas volume flow rates, this temperature, 477 degrees Celsius, is the average resulting temperature. Using the heat capacity rates and the respective inlet and outlet temperatures, the actual and maximum potential rates of heat transfer are solved for, and which come out to 2,612 watts for actual and 5,768 watts for maximum potential. By extension, we can now solve for the heat exchanger effectiveness, which comes out to 45.3%. ANSYS fluent was used to determine the most adequate method of mixing two fluids of different temperatures and flow rates. Our selected mixing methods consisted of baffles and grates. Using ANSYS fluent for flow simulations proved a tricky task. The software has a very large learning curve, and several tutorial videos assume the viewer has already had extensive experience with the unintuitive interface. Additionally, education licenses prohibit use of meshes whose element count exceeds 512,000. This issue has been addressed with Dr. Issa and the IT department. However, we have not heard any word back from the customer support from ANSYS as far as rectifying this licensing issue. This problem has led us to using two-dimensional surface meshes where we could. These provided adequate results as seen in the next slide. For three-dimensional simulations, we used SolidWorks. Here we see two examples of these simulations. The picture on top depicts baffles in 2-inch increments, and the picture on the bottom depicts grates in 2-inch increments. As we can see, the baffles provide a more effective and efficient mixing method than the grates do. Mixing these fluids in the least space possible is important to our design parameters.
So the previous method of manually lighting the combustion decreased the level of safety as well as the project's marketability because it was being manually lighted. To solve this issue, the group decided to incorporate a spark plug that is controlled by an Arduino board that would be switched on from a much safer distance. The board was then coded to turn the spark plug on for 100 milliseconds and then off for 100 milliseconds and so on until the flame was ignited and the switch could be turned off. We made sure to do some testing to decide the appropriate distance the component would be placed to keep it from being damaged, but also close enough to avoid too much of a hydrogen buildup. Another benefit of the placement is that the water would also help cool the component while it's being ran. Another important consideration in moving forward with our project is to make sure that the thickness of our pipe wall was able to handle the stress that would be occurring due to the pressure of the combustion. So we took a pressure that was experiencing, which is 72 psi, and plugged it into our thickness minimum equation that we found, and that came out to be 0.009 inches, and that is obviously much less than our pipe that we ended up choosing of a thickness of 0.085 inches. And then we took those values and plugged them into the working stress equation as seen, and that came out to be 5.85 megapascals, which is approximately 847 psi. During our research, we found this quote that a typical material for small water-cooled combustion chambers is copper, which is what we're using, and that has an allowable working stress of about 8,000 psi, which is way more than our chamber's experiencing, so we felt very pleased by these numbers.
We then calculated the thermal resistance of our double pipe heat exchanger. The dimensions of the pipe are given above. The inner diameter equal to 2 inches, outer diameter equal to 2.125 inches, and the length of the copper pipe equal to 12 inches with a thermal conductivity of 401 watts per meter Kelvin. For the areas where the cold fluid and hot fluid will be traveling by, we calculated the inner area to be 0.049 meters square and the outer area to be 0.052 meters square. And as for the heat transfer coefficients, we solved HI equal to 3.433 watts per meter square Kelvin and HO equal to 1,765 watts per meter square Kelvin. With these values, we were able to solve the thermal resistance equal to 5.999 Kelvin per watts and the overall heat transfer coefficient equal to 1.768 times 10 to the power of 3 watts per meter square Kelvin.
The customer required this assembly to be designed for in the final product. This is to ensure that separate components can be redesigned, built, and installed with no issues. The customer considers this a research prototype that will both provide data and a template for future expansion in the scope of the project. Here in the diagram, we see all the different major components. Machining and welding of the steel components went relatively unhindered. Welding of the copper components, however, provided problems due to the unique problem and geometry of the issue. While brazing is typically used to fuse copper pieces together, high operation temperatures provided uncertainty as to the effectiveness of this method. Ultimately, it was decided that silicone bronze would be used to TIG weld all the copper components together. Welding with silicone bronze is a risky venture due to the toxic fumes it emits. However, the welder took precautions to weld the copper pieces together successfully with no other issues. And here is a picture of our final build, where we have here the main combustion chamber, followed by the transportation and delivery nozzle. Up here in the combustion chamber, we see up here in white the spark plug. Over here, down here, we see the nipple that is used to attach the feed water pump. Right here is a coupling that connects both the heat exchanger with the mixing chamber. Right here we have a reducer and a nipple welded onto the mixing chamber. The nipple is threaded to connect the steel braided hose. Using several adapters, we finally come to our exit nozzle.
And now here we have two tables that shows our bill of quantities for our project. This table shows the materials purchased for the combustion chamber, and this table shows the list of materials used for the transportation and delivery system. The materials listed on both of these tables were all purchased locally here in the Amarillo, Texas area. Our total budget provided by our customer was $2,000, and as you can see down below, we were able to remain well under the budget with our cost, resulting at a price of $1,114.
So our final manufactured piece was intended to be used horizontally. In our simulation, we expected a continuous cycle of the water as it was injected, but once we were doing the experimentation, we observed only 2 cycles of the water before there was actually pooling that was occurring at the bottom of the chamber. So we decided to combat this issue by orienting our project in a vertical manner and act as a boiler so that the water would take the time to evaporate, and this actually ensured equal cooling along the length of the chamber as well, so it worked out perfectly fine. In doing this, however, it did raise another issue. The original method of connecting the heat exchanger and the mixing chamber were pipe flanges. These were deemed to be too heavy, considering we were using a vise to hold our project upright. Thus, the experimentation only included the heat exchanger and not the mixing chamber. Unfortunately, our customer was unable to provide more time to do further experimentation due to some personal pressing matters.
2 different temperature readings were taken. One of the cold steam outlet, which came out to 189 degrees Celsius, and one a foot above the outlet, where a rough estimate of the mixed steam temperature was found. This temperature came out to roughly 252 degrees Celsius. We can now compare these readings to the theoretical values we found. The mixing simulation provided a mixed steam temperature of roughly 282 degrees Celsius. Along with the theoretical desire to completely evaporate the feed water at 152 degrees Celsius at its respective saturation temperature, we can find the percent errors of the cold and mixed steam temperatures. The percent error for the cold steam comes out to 24.3%. The percent error for the mixed steam comes out to 10.6%.
And now we have some recommendations for future experiments. First, applying threads around the outer surface of the copper pipe would encourage more of a circular controlled water flow, and using a corrosive resistant material for the outer shell due to the water, as well as needing a longer, higher temperature rated transportation hose depending on the application used. And lastly, extending the progress in the project to experiment and analyze nozzles and the different geometries of spray delivery they have to offer.
This project forced us outside of our comfort zones in several different ways. The complexity of the problem to be solved required extensive literature review and unique problem solving to achieve the desired results. We learned the importance and utility of using clean energy where possible. We learned to communicate with each other as well as several different other people and organizations with different backgrounds and levels of expertise. We learned the importance of trying every possible alternative to produce the best results. We learned when to lead the project and when to listen to others and compromise. We learned various experimentation procedures and guidelines, always putting safety of ourselves and each other first. We learned to accept feedback, recommendations from reports, faculty, and builders to ensure the project could become as successful as possible. We would like to thank all the faculty who were involved in the success of this project, as well as the student body that was helpful, and Charlie's Machine and Welding. Thank you all for your time. We look forward to hearing your questions in the FAQ, and have a good day.